Hello my dear students. Welcome to EPG Pathshala. I am Anchal Srivastava from Banaras Hindu University. Today we are going to discuss about the module Carbon Nanotube and Introduction from the paper Nanoscience and Technology 2. After studying this module, we shall be able to learn a basics of carbon material research along with their historical introduction. You shall be able to know the different form of allotropes of carbon and some basic definition, structure and type of nanotubes. Carbon nanotubes are remarkable objects. They may revolutionize the technology in near future. Tomorrow, society will be shaped by nanotube application, just as silicon-based technology dominates society of today's. Space elevators can be possible by the strongest cable, hydrogen-powered vehicle, artificial muscles. These are just few examples of technological marvels that may be made possible by emerging science of carbon nanotubes. Of course, this prediction is still some way from becoming reality. We are still at the stage of evaluating possibilities and potentials. Consider the recent examples of fullerenes, molecules closely related to nanotubes. The anticipated surrounding these molecules, first report in 1985, result in the form of Nobel Prize to Kerr, Kroto and Smalley for their discovery in 1996 in chemistry. However, a decade later, few applications of fullerenes have reached to the market, suggesting that similarly enthusiastic predictions about nanotubes should be approached with caution. There is no denying, however, that the expectations surrounding carbon nanotubes are very high. One of the main reasons for this is to anticipated application of carbon nanotube in electronics. Many believe that current technology for miniaturization microchips about to reach their lowest limit, and that nanotube based technology are the best hope for future miniaturization. Carbon nanotubes may therefore provide the building block for future technology, enhancing our standard of living. In this module, we describe the historical overview, carbon allotropes, especially nanocarbon allotropes, and their structures of carbon nanotube, where I am going to discuss the introduction of carbon nanomaterials. Carbon nanomaterials got attention by the discovery of C60. C60 is known as fullerene. This fullerene was predicted by E.G. Osawa, Toyohashi University of Technology in 1970. However, this is also proposed by R.W. Henson, the structure of C60, but it was not accepted, and result was acknowledged in carbon in 1999. Then in 1973, scientists from USSR by Professor Bochwer made the quantum chemical analysis of the stability of C60 and calculated their electronic structure of this molecule. In 1992, fullerene was found in a family of material and known as sungites in Russia. And in 2010, fullerene has been discovered in cloud of cosmic dust surrounding a distant star 6,005 light years away. I will give the brief history by the name of which this molecule C60 is called fullerene. The fullerene is given by the name of the scientist Buckminster Fuller. Buckminster Fuller is basically an architect who designed this molecule structure. He born in 1895 in the United States and died in 1983 at the age of 87. He had children Elgara Fuller, Cinderella and Alexandra, who died in childhood. As you know, fullerene is a cage-like structure where 60 carbon atom makes a structure like a football. This football contains 12 pentagon and 20 hexagons. This structure can be elongated by addition of another hexagons, and other stable fullerenes are C70 and their other isomers. The C70 also contains 12 pentagon because it is needed to close the structure, and for other elongated structure of fullerene, additional hexagons should be added to give a structure which is close to tubular. This nanotube is actually form of, if you cut this fullerene by half, then half capping from one side and another half capping from the second side should close the structure of nanotube and form a elongated structure, and which is in actually called nanotube. I will discuss this thing in detail later. So let us talk the roadmap of this fullerene and their allotropes, especially in nano dimension. As I told you that fullerene got attention in 1985, and after their discovery, three scientists, Carl, Croto and Smalley, got the Nobel Prize in 1996. So this molecule is aromatic in nature and form a variety of structure, shows a very exciting properties and therefore application, especially in chemistry. As I discussed to you earlier, that fullerene can be extended in form of tube, and this tube has first discovered in 1991 by Sumo Ijima, a Japanese scientist. This tubular structure, of which is known as carbon nanotube, is got a long attention because this has behaved like a quantum wire. The earlier one, which is fullerene, is as a quantum dot. This quantum wire, which is nanotube, shows remarkable electronic properties and which can be changes because of the chirality and dimension from metallic to semiconducting, open a new era of nanotechnology and nanoscience research. Again, there are a very recent discovery came in 2004 as a graphene. This graphene, if you see the single layer of graphite with the sp2 hybridized structure, in that case the sheet which we will get, one atom thick, is nothing but graphene. This graphene again shows lot of quantum properties, and these properties make them very exciting for study of quantum 2D system. This 2D system opens again a new era of visualizing all the predicted quantum mechanical theories. Therefore, Geim and Novoselov got the Nobel Prize in 2010. There is many more undisclosed discovery still lying in the pipeline in future, and this is maybe because of this sp and sp2 hybridization. New structure can open a new dimension in carbon nano research. Let us discuss the discovery of carbon nanotube. Carbon nanotube was discovered by Sumo Ezima in 1991. This carbon nanotube is a tube-shaped structure or material made up of carbon with a diameter of nanometer scale. However, their length is micron in size. Even today, people are able to grow in millimeter size. So, the object with nano dimension with diameter and length in micron has been reported. A nanotube is 1/1000th of a meter, or about 10,000 times smaller than human hair. So it is really a material which cannot be seen by our eyes, and therefore microscopes are needed to see it. Our carbon nanotubes has many structures. They have a different length, thickness and number of layers. I will discuss the construction of carbon nanotube. As I discussed already, the structure of fullerene, where we have a closed-like structure. But in case of carbon nanotube, if we take a graphene sheet, and in this graphene sheet, we can put this every carbon atom, if I nomenclate them with a vector point, which is, I can say, if I take a vector and this vector has CH, then CH is equal to NA1 and MA2, where A1 and A2 are the two small vectors shown in the figure. Vector A1 and A2 have a particular direction, and M and N are two integers, and this integers we can choose it like 0, 1, 2, 3, etc. If I want to put each and every carbon point as one of the vector, then this CH vector, if I put it like 5 N1 and 0 M2, in this case I can only put the numerical value which is 50 and denote one particular carbon atom, and therefore in that case you can see easily that every carbon point has carbon atom has been identified by the numerics like 10, 20, 30, 40 or 11, 22, 33, 44, etc. This is needed because this graphene sheet or this carbon nanotube structure doesn't come in the known crystal system like cubic, hexagonal, rhombohedral, etc. So we have to explain this nanotube in a different way, and this is the way which I am trying to explain to you. So now in this case, if this chiral vector, for example 80, if I want to make a tube, then the head of the vector, if I match it with the tail of the vector as a circumference, then the tube which we will get is known as 80 tube. Or if I take the 5 and if I take the head of the tube and match it with the tail of the circumference, then we will end up 50 nanotubes. This chiral vector C and the angle between them theta are two important parameters which is going to define their diameter and other properties. I want to mention here is that A1 and A2 is the two vectors from carbon-carbon distance, which is shown in the figure. In this way, we will end up, as you can see here by the structure, one can determine the diameter of nanotubes and chiral vector of carbon nanotubes. This is based on carbon-carbon distance and the integer which we used, n and m. So one can find the equation for determining the diameter of carbon nanotube as d is equal to c by pi, where c is the chiral vector. As I discussed already, this c is equal to n a1 plus m a2. So one can write under root 3 acc in bracket m square plus nm plus n square to the power half by pi. So one can see here is that diameter can be calculated mainly on mn values and carbon-carbon distance. Therefore, one can get variety of single wall nanotube of different diameter. One can also calculate the chiral angle of nanotubes by the equation theta is equal to tan inverse under root 3m by m plus 2n. One can see here again that this is only based on m and n value. This chiral vector can be between 0 to 30 degree. If anyone can go beyond 30 degree, then repetition takes place. Therefore, one can find the value of theta with this equation, which is nothing but the chiral angle for nanotubes. Which I want to show that how our 50 tubes or how our 55 tubes and how our 14-5 tubes can be looks like. So for example, there is a family of the tube which are where m is 0. For example, 50, 80, 90. So m is 0, and there is another class of tube where n is equal to m. For example, 4, 4, 5, 5, 7, 7, 9, 9, etc. And then the third class where n and m is not equal to 0. For example, 14, 5. So if you see, then all these three, the major difference is that the carbon-carbon bond is perpendicular to the tube axis in case of armchair, like 5, 5, 6, 6, or something like that. And in case of zigzag tube, which is m is equal to 0 case, and in that case, the tube axis is parallel to the carbon-carbon bond. However, in the third tube, which is known as chiral tube, this tube axis of carbon-carbon bond is neither parallel nor perpendicular. So we will get three different kind of single wall carbon nanotube: zigzag, chiral, and armchair. And I have explained their construction, how they are made up of this tube. Similarly, I can show that there is a possibility of growing tube inside tube. So if you put one tube and there is another tube inside and there is two walls, then it is called double walled carbon nanotube. And if you put more than that, for example 6, 10, 20, then these nanotubes are called multi-walled carbon nanotube, and this is very exciting for different properties. So which gives them their strength as well as many other new properties. So depending on the chirality, where I have discussed that carbon-carbon bond is parallel or perpendicular, or either not parallel nor perpendicular, it is showing different electronic behavior. Some can be metallic, some can be semiconducting. And this will open a new area that a single material can behave like insulator to metal to semiconductor. And this open a new area of research in carbon based technology. The same thing can be explained and can be shown here, that how this ABC looks like, and the tube structure you can see very easily is perpendicular to the carbon-carbon bond, where there is a tube axis which is parallel to the carbon-carbon bond, and in this case chiral were neither perpendicular to parallel. So this is ABC, is these three examples of armchair, zigzag and chiral structure of nanotubes. Once again, carbon nanotubes are nano in dimension, and therefore it is not possible to visualize our naked eye. In that case, we need a sophisticated techniques to study this nanotube structure. And presently we have systems where this nanotube can be imaged. Scanning electron microscope is one, transmission electron microscope is the other one, then atomic force microscope and scanning tunneling microscope are the new microscope which are developed. Is we can visualize our nanotube along with that. So the picture which is shown in A is the low magnification of scanning electron microscope, where you can see the bundle of carbon nanotubes is visible. In DEF, you can see the transmission electron microscope images of the bundle of SWT single walled carbon nanotube. Then there is another view where you can see very easily the tip of the nanotubes, where you can see that they are single walled carbon nanotube which is open-ended in nature. And then the diameter can also be visualized, which suggests that this bundles is of the size 0.315 nanometer. High resolution TEM studies also suggest the formation of double walled carbon nanotube through ACM and TEM, and atomic force microscope in the figure JKLM has shown, where we can also measure the height profile. So this way the height of that nanotube is 1.5 nanometer and width is around 120 nanometer, shown in this figure. And STM data also suggests that this nanotube has some trace amount of nitrogen and phosphorus and can be visualized using EDAX mapping and things like that. So these are the techniques by which we can very easily see the different kind of nanotubes. They are made up of single walled or double walled or multi-walled, what are their dimensions, what are the other atoms or molecules or things are encapsulated inside the system. This can be visualized using this technique. So dear students, let us summarize what we have learned in this module. As I discussed, that fullerene, which is C60, is a three-dimensional network of carbon atoms containing pentagons and hexagons. But it is named as Buckminster-Fuller. We need 12 pentagons to close the structure and make this structure like football like. 12 pentagon is required and 16 hexagons are required for C60. However, if we want to go for other similar structures of fullerene, we need 12 pentagon in every case and more number of hexagons is required for becoming bigger structure. The carbon nanotube is nothing but the extended form of this fullerene, where half fullerene is kept at one end and the other half fullerene is kept at another end, and rest the hexagonal structure which is slightly distorted to form the tube. Carbon nanotube was discovered in 1991 by the Japanese scientist Sumo Iijima. There I want to add that two postdocs, Professor P. M. Ajjan and Professor Ibesen from was working with him and have seen this structure in microscope. These nanotubes are of two kinds. One is single wall carbon nanotube and the second one is multi-wall carbon nanotube, which I have explained in detail in previous slides. The properties of these nanotubes depends on their chirality, how this graphene should be rolled to form armchair, zigzag and chiral structures. One can find the diameter of tube based on their chiral vector, which is C is equal to Na1 plus Ma2, and this M and N are the integer. However, ACC is the distance between two carbon atoms. So one can find this diameter D is equal to C, which is chiral vector, divided by pi, are equal to under root 3 ACC m square plus nm plus n square to the power half by pi. And depending on the value of n and m, every tube has their different diameter. We can also find the chiral angle. Chiral angle can be found by the equation theta is equal to tan inverse under root 3 m by m plus 2n, by which putting the value of m and n we can find out the chiral angle. This chiral angle can be in between 0 to 30, because if we go beyond 30, repetition takes place.